We've spent the past 2 lectures talking about vector line integrals of a vector field over a curve. Last time, we saw that if the vector field f was conservative, then there were several tricks that allowed us to simplify the calculation of a vector line integral. But what if f isn't conservative? Are there any other cool shortcuts? Today we're going to look at a special one that applies to any vector field, but specifically to vector fields over closed contours. So let's begin today with a calculation. Let's compute the line integral of any vector field f over a closed contour, where I'm going to make one assumption on the contour. Specifically, we're going to assume that C is closed, simple, and positively oriented. Closed just means that its initial point is the same as its ending point. So an example of a not closed curve would be something like this, where the initial point and the final point are different. Simple just means the curve doesn't self-intersect. So an example of something which is not simple might be a figure 8 curve, where the curve crosses itself at some point in the middle. And finally, positively oriented just means that the flow around the curve is, roughly speaking, counterclockwise. So something who would be negatively oriented would be a curve whose sort of global rotation is clockwise as opposed to counterclockwise. So under these 3 assumptions, could we in fact calculate the line integral of any vector field whatsoever? The amazing thing is yeah. Let's start off by writing the vector field in terms of its components. Let's say that the vector field has 2 components. It has a component u, and its second component is v. So this is just another notation for the line integral. Notice that we could actually split this up really into 2 separate line integrals. There's the line integral of u dx over the curve C, and then there's a line integral of v dy over the curve C. Normally we don't split these things apart, but right now I'm going to attack these things in sort of 2 separate pieces. Let me focus on this part first and see what damage I can do to calculating this. Over here at my contour C, let's take the extreme leftmost point, which might occur at, say, x equals a, and then we'll take the rightmost point at x equals b. The bottom arc of our contour could be expressed as a function, say f equals c of x. And let's say that the top part of our contour right here is the graph of some other function, y equals d of x. That means that this integral over a closed contour could be broken apart into 2 smaller non-closed contours. There's the integral over the bottom piece, u dx, and then there'll be the integral over the top piece, u dx. And so we can attack this as 2 separate non-closed line integrals. Let's focus on the bottom arc first, because the bottom arc is pretty easy to parameterize. Since it's the graph of a function, we can use the usual parameterization t equals x and y equals c of x or c of t, and then this parameterization will be valid. Well, let's see, the extrememost x value or t value is a, and the rightmost t value or x value is b. So this would become our parameterization. And so the integral over this bottom segment of u dx is going to be the integral of u evaluated along the curve, t of c of t, times the derivative of the x term, which is just 1, dt, evaluated from a to b. On the other hand, if we focus on the top part, well, the top curve can be parameterized by x equals t and y equals d of t, where the timer goes between a and b, just like it was before. Unfortunately, this parameterization parameterizes the curve from left to right. And so if we wanted to go and do the integral over the top part of u dx, we'd have to go and take the negative of the integral we would get from a to b, since the parameterization is in the opposite order. But other than that, the argument would be the same. We would have u evaluated on the second curve, t comma dt, times the derivative of x, which would be 1 dt. And so we can add these 2 results together, and what we find is this: that the closed integral of u dx is the same thing as is the integral from a to b of u of t comma c of t dt plus negative the integral from a to b of u of t comma d of t dt. Note that this can be written as a single integral, the integral from a to b of u of t comma c of t, minus u of t, comma, d of t, dt. Or, if I pull a negative out, negative the integral from a to b of u of t dt minus u of t c of t dt. This expression inside the thing that we're integrating right here could be written like this. It's just the function u of t comma y evaluated from y equals c of t to d of t dt. Because that's usually what we use for this notation. But this part right here looks like the last part of the fundamental theorem of calculus. If I focused on just the expression on the inside, this would be exactly what we get if we were to integrate the derivative of u with respect to y of ty dy evaluated from y equals c of t to y equals d of t. Because if we were to integrate the derivative with respect to y, we would just get u evaluated from the top part to the bottom part. Now, keeping the rest of the stuff around us, we would have this. And so, we've shown that the closed integral of u dx is equal to the iterated integral negative the integral from a to b of the integral from c of t to d of t of del u del y of ty dy dt. But notice that every iterated integral, something like this at the bottom, by Fubini's theorem represents a double integral. Specifically, it represents the double integral of the function del u del y dA over the region R, where R is described as saying that the x values stay between a and b, and that the y values stay between c of x and d of x. What exactly is this region? Well, it's a vertically simple region where the y values go from c of x to d of x, so this range in between here, and the x values go from a to b. In other words, this region R is nothing more than the inside of the curve. If we summarize this, we've shown that the closed contour integral around the curve C of the function u dx is exactly the same thing as negative of the double integral of the region inside the curve of del u del y dA. A similar argument would show that this ends up being the same thing as the integral of del v del x dA, positive, where we're still integrating over the inside of the curve C. And so from beginning to end, we've shown that the integral of f over a closed, simple, positively oriented curve is equal to the double integral of the function del v del x minus del u del y dA, where this integral is taken over the inside of the region C. This result is known as Greens Theorem. Let C be a simple, closed, positively oriented curve, and R denote the region inside of that curve. If f, whose components are u and v, is any vector field in R2, then the closed vector line integral of u dx plus v dy is equal to the double integral over the region R of the scalar function del v del x minus del u del y. Verify Greens theorem for the vector field f equals xii plus xj, and t the triangular curve with vertices at the points 0, 0, 1, 0, and 0, 1. In other words, to verify Greens theorem, we would like to show that the two parts of Greens theorem are the same. In other words, if we take the vector line integral over this triangular region, that would be the same thing as the double integral over the inside of the triangle of the function del v del x minus del u del y dA, where u and v are the component functions of the vector field f. Now notice that our vector field f has been expressed in terms of the standard basis. For us, the vector field is going to be xy comma x, and so that tells me that u is being played by xy and that v is being played by x. So we have just two different line integrals to go and worry about. Let's focus on, well, the line integral first. So let's see what the curve looks like. It says it's a triangular curve with vertices at the point 0, 0, 1, 0, and 0, 1. So it's this triangular curve right here. For Greens theorem, it has to be a simple, closed, and positively oriented curve. So it has to be moving like this. Now, if we wanted to go and work out the integral of f dot ds over this triangular shape right here, notice that each part of the triangle could be parametrized separately. The straight line arc here, the straight line arc here, and the straight line arc here. So we could break this up into three separate line integrals. The line integral of f dot ds over a, plus the line integral of f dot ds over b, plus the line integral of f dot ds over that hypotenuse c. And we'll just do three separate calculations. So let's focus on the first part, the straight line segment that goes down from the point 0, 1 to the point 0, 0. That's a straight line, so we can approximate it, or we can parameterize it quickly with the formula xy equals the starting point 0, 1 plus the vector who goes from 0, 1 to 0, 0, which is 0 minus 1, times t. And so we're going to have x is equal to 0 and y is equal to 1 minus t. This will be valid as long as time stays between, well, let's see, when time is equal to 0, we're at the point 1, 0, and when time is equal to 1, we're at the point 0, 0. So our first integral, the integral over a of f dot ds. Now, since the vector field f is given by xy comma x, we can also write this as xy dx plus x dy. This is just another notation for the vector field, but it does make it easier to sort of plug in our various component functions into this. This will become the integral from 0 to 1 of x, which is 0, times y, which is 1 minus t, times the derivative of x, which is 0, plus x, which is 0, times the derivative of y, which is minus 1 dt. So this is simply the integral from 0 to 1 of 0 dt, and that's going to evaluate to 0. So our first integral evaluates to 0. Now let's focus on the second integral, the integral over the straight line segment b. So to parameterize this, since it's another line segment, we'll use the same basic trick. It's the starting point 0, 0, plus the vector who moves from 0, 0 to 1, 0, which is 1, 0, times the time variable t. So our x value is simply going to be t, and our y value will be 0. So if we want to go and integrate f dot ds over the curve b, that's the same thing as integrating the vector field xy dx plus x dy over the curve b. So we're going to integrate from 0 to 1 our time parameter, x, which is t, times y, which is 0, times the derivative of x, which is 1, plus x, which is t, times the derivative of y, which is 0, dt. And so once again, we get another integral from 0 to 1 of 0 dt, which will evaluate to 0. And so our second integral is 0. Finally, let's focus on that hypotenuse. So that's the straight line curve who goes from the point 1, 0 to the point 0, 1. So if we parameterize this chunk, we're going to take the starting point 1, 0, plus the vector who connects 1, 0 to 0, 1, which is minus 1, 1, times the time parameter. So our x equation will be 1 minus t, our y equation will be t, and this will be valid as long as t stays between 0 and 1. So the integral of the vector field xy dx plus x dy over the contour c will be the integral from 0 to 1 of x, 1 minus t, times y, t, times the derivative of dx, minus 1, plus x, 1 minus t, times the derivative of y, 1 dt. And so if we clean this up, we're going to get the integral from 0 to 1 of, let's see, we have negative t to distribute into there, so negative t minus negative t squared plus 1 minus t dt. Well, let's see, that's the integral from 0 to 1 of t squared minus 2t plus 1 dt. Actually, that's just t minus 1 quantity squared dt. If I integrate that with a quick substitution, we're going to get 1/3 t minus 1 cubed evaluated from 0 to 1. If we plug in 1, we're going to get 1/3 times 0 cubed. Take away, if we plug in 0, we're going to get 1/3 times 0 minus 1 cubed. So the first piece cancels. In the second piece, we have negative 1/3 times negative 1, or positive 1/3. So that's the line integral over the third stretch. If we add our results together, we get a grand total of 1/3. So the line integral evaluates to 1/3. Now let's focus on the double integral. Now for the double integral, I'm focused not on the curve, but on the region inside of it. Now notice that the region inside of it is a nice vertically simple domain, and so we could describe this by saying that, well, the y values always stay above the x-axis, which is the curve y equals 0, but they stay below this top line. Notice that this is a line that has a y-intercept of 1 and a slope of -1. So it always stays below the curve 1 minus x. The corresponding x values have to stay between, well, the leftmost x value would be 0, the rightmost x value would be 1. And so here's a description of this particular region. So then the double integral of the inside of the triangle of the function del v del x minus del u del y dA, well, let's see, that's going to be a double integral of the function del v del x. Well, if we take the derivative of x with respect to x, we're going to get 1, minus del u del y. If we differentiate u with respect to y, we're going to get x. So this is the function we're integrating over the triangle dA. Because we have the region expressed as a vertically simple domain, Fubini's theorem can be applied to say that we can integrate the function 1 minus x with respect to y first between 0 and 1 minus x, and then with respect to x next between 0 and 1. So now we're doing a good old-fashioned double integral iteration. We'll focus on the inside part first. The integral from 0 to 1 minus x of 1 minus x dy will be, well, 1 minus x is a constant, so it comes along for the ride. We'll get 1 minus x times y, evaluated from 0 to 1 minus x, which gives me a grand total of 1 minus x quantity squared. So now we need to go and integrate this expression. And so we'll integrate from 0 to 1, 1 minus x quantity squared dx. Now this is another good candidate for u substitution, and if we do that, we're going to get as an antiderivative 1 minus x cubed over 3 times -1, evaluated from 0 to 1. Now, if we plug in 1, we're going to get -0 cubed over 3. If we plug in 0, we're going to get minus 0 times 1 cubed over 3. And that's 1/3. And so we found that the double integral also evaluates to 1/3. And so we verified Greens theorem, that both the line integral and the double integral are the same. Compute the closed line integral of f dot t ds over p, where f is the vector field y, 2x squared, and p is the pie-shaped periphery shown below. Now, the first thing to notice about this is, even though it's a ds with no arrow over the top, this isn't a scalar line integral. This formula right here, f dot t, was actually nothing more than our formula for what f dot ds is. So this is just one of the other notations that we use for a vector line integral. So now I know it's a vector line integral. If I wanted to treat it as a vector line integral, I would need to parameterize this pie-shaped sector right here. Well, just like last time, I can do each of the 3 pieces individually, and so I could break this down into 3 separate sections. But I don't want to do that. Partly because I'm lazy, but mostly because the region inside that contour is so nicely described by polar coordinates. It would be far easier to do a single double integral over the inside region of the function del v del x minus del u del y dA than it would be to do 3 separate line integrals. So we'll simply apply Greens theorem and turn this line integral problem into a double integral problem. So we need to go and do a double integral over this little pie shape of the function del v del x, which would be 4x, minus del u del y, which would be 1 dA. So now all we need to do is describe this region. Well, this region is really easy to describe in terms of its polar coordinates. The radii will always go from a minimum radius of 0 to an outer radius of 2. On the other hand, the angles theta involved, well, the smallest angle theta will be 45 degrees. The largest angle theta will be 45 degrees in quadrant 2. And so our theta will go between a minimum of 45 degrees and a maximum of 135 degrees. And so we've got this region described in polar coordinates. So using our change of coordinate formulas, this will become an iterated integral. We're going to integrate r, the scaling factor for polar coordinates, times 4x, r cosine theta, minus 1 dr, where r goes from 0 to 2, and then iterate that, integrating it from theta between pi over 4 and 3 pi over 4. And so if we clean this up, this becomes the iterated integral of pi over 4 to 3 pi over 4 times the integral from 0 to 2 of 4r squared times the cosine of theta minus r dr d theta. And so we don't have to do any kind of line integrals or parameterizations whatsoever. Let's first focus on this inside iterated integral. Getting an antiderivative with respect to r, we would have 4/3 r cubed times the cosine of theta minus 1/2 r squared, evaluated from 0 to 2. So if we plug in r equals 2, we're going to get 4 times 8, or 32/3 cosine of theta, minus, when we plug in r equals 2 here, we'll get half of 4, or 2. When we plug in 0, we're going to get 0 over 0, and so that's our iteration. We're going to integrate from pi over 4 to 3 pi over 4 the function 32/3 cosine of theta minus 2 d theta. Let's carry that work up here. If we integrate this expression with respect to theta, the integral of cosine is sine, so we'll have 32 times the sine of theta minus 2 theta, evaluated from pi over 4 to 3 pi over 4. So plugging in the top values, we're going to have 32/3 times the sine of 3 pi over 4 minus 2 times 3 pi over 4. When we plug in the bottom limit, we'll have 32/3 times the sine of pi over 4 minus 2 times pi over 4. So if we clean that up, that's going to be 32/3 times the sine of 3 pi over 4, which is root 2 over 2, minus 6 pi over 4, minus 32/3 times the sine of pi over 4, which is root 2 over 2, minus negative 2 pi over 4. So these two expressions cancel. And on the other hand, we're going to have 6 pi over 4 negative plus 4 pi over 4. That'll get us a grand total of negative 4 pi over 4, or negative pi. And so there would be our value. One of the things we mentioned in the last podcast was that if the domain of f was simply connected and f satisfied the gradient test, then f needed to be a conservative vector field. We can use Greens Theorem to prove this particular statement. To see this, let's suppose that this is the domain of f, which is a simply connected set, so there's no holes or punctures on the inside. I want to show that f is conservative, and so let me go and take some closed contour inside this set right here. And we'll work out the integral of f dot ds over this tiny contour on the inside. According to Greens' theorem, this is going to be equal to the double integral of the second component of f, derivative with respect to x, minus the first component of f's derivative with respect to y, dA, over the inside of the region C. Well, we've been told that f satisfies the gradient test, and in 2 dimensions the gradient test is the statement that del f1 del y is equal to del f2 del x. But if that's the case, then this difference has to be 0, and so we're integrating the function 0 dA over some region. So this is the volume underneath the surface of height 0 over the region A. That's going to evaluate to 0. And so we've shown that this evaluates to 0. Where did we use the whole idea of being simply connected? Well, we're using the fact that once we draw this curve right here, that the domain of f still lives inside this, that there's no point where this particular formula would fall apart. So it's used in a subtle spot. We've seen that Greens' theorem allows us to turn certain double integrals over simply connected regions into line integrals around their positively oriented boundary. Specifically, if we take a double integral over this region of del v del x minus del u del y dA, that's the same thing as the closed line integral over this curve of the vector field u dx plus v dy. What would happen, though, if the region was not simply connected? What if the region itself had holes? Then we would have 2 more sections of its boundary. Is it possible to modify Greens' theorem this way? Actually, it kind of is. Essentially, to do a double integral over this big shape, you do the double integral over the entire region, and then you would subtract the double integrals over each one of the tiny shapes. Now, the double integral over the big region would be the same thing as doing the line integral over the counterclockwise oriented boundary by Greens' theorem. And each one of these double integrals would be the same thing as doing line integrals over these guys counterclockwise. But then you would subtract them. Well, if you subtract the line integral over a curve, that's the same thing as adding the line integral of the curve with the curves going in the opposite orientation. So these interior curves would actually be moving clockwise. In essence, the basic rule for using Greens' theorem is that if you have a region, say this region right here, and you wanted to turn it into a line integral, then Greens' theorem is valid as long as we orient the boundary pieces the appropriate way. Now, the outermost edge of the boundary is always oriented counterclockwise. But how do we figure out the orientations on the inside? Well, the general rule of thumb is that you orient the curves in such a way so that the region is always to the curve's left. So, for example, when we're on the outer edge, if we were sort of moving along the curve from left to right, the curve would be at our edge, our left side. So if we're on the inside, then we would have to be moving clockwise, because that would be the way to keep the curve to our left. If we were on this little innermost segment right here, well, then we would be moving counterclockwise again. And so if we wanted to turn this into a double integral, then this would be the complicated curve that we would integrate over with the appropriate arrows in their place. An interesting consequence of this is that if we were to take a region in the plane and orient its boundary appropriately and integrate the specific vector field negative y dx plus x dy over this boundary, then according to Greens' theorem, that would be the same thing as doing the double integral over the region itself of the function 1 minus minus 1, or integrating the function 2 delta a. Now remember that constants can be pulled out of double integrals, so if I pull this out to the front, we'd be doing twice the double integral of 1 dA. But the double integral of 1 dA over some region, that's exactly the area of this region. And so what we found out is we found out this, dividing both sides by 2, that the area of any plane region R is always equal to 1/2 the line integral around the oriented boundary of R of the expression negative y dx plus x dy. So in other words, it's possible to compute the two-dimensional area of a region by looking only at a line integral along its outer edge. You might have noticed in the past couple of podcasts that we've needed to keep track of certain partial derivatives of certain functions in certain orders. For example, in Greens' theorem, we need to take the partial derivative of the second component with respect to the first variable minus the derivative of the first component with respect to the second variable. Or we did the gradient test for a function of 3 variables. We needed to have the equations del f1 del y equals del f2 del x and del f3 del x equals del f1 del z and del f3 del y equals del f2 del z. Are there any ways to sort of help remember the order of these particular things right here? Well, it turns out that there's a clever little trick to help us get the order of these expressions correct. The idea is that we're going to define a new symbol, nabla by itself. And nabla by itself is going to be a vector, but it's not going to be a vector of numbers. It's going to be a vector of partial derivative operators. So if we thought of this thing as a vector and we multiplied it against a scalar, well, how does vector scaling work? Well, you scale each one of the components by the scalar. And so if we were to scale the vector by f, then we would have del del x f, del del y f, del del z f. Of course, I can interpret each of those as being partial derivatives fx, fy, fz, and so we've recovered the gradient But this was only one of 3 different vector products we looked at. What happens if you took this nabla, which is sometimes called the del operator, and you crossed it with a vector field? What would this be? Well, let's work it out real fast. We'll take del cross f. So to do a cross product, we need to make the first column the standard basis vectors. The second column will be our del operator, del x, del y, and del z. And then our third column will be the vector field f. So let's say it has components f1, f2, and f3. So if we work out this, we're going to have the vector I times the submatrix del y, del z, going across the columns, f2, f3, minus j times the determinant of the submatrix going by the columns del x, del z, f1, f3, plus k times the determinant of the submatrix going by the columns del x, del y, f1, f2. And so if we work this out, we're going to have I times del y times f3, or del f3 del y, minus del z times f2, or del f2 del z, minus j times, across the main diagonal, we'll have del x times f3, or del f3 del x, minus del z times f1, or del f1 del z, plus k times del x times f2, or del f2 del x, minus del y times f1, or del f1 del y. If you notice, each one of these expressions are exactly the expressions needed in the gradient test. So we've actually just shown this, that a vector field f satisfies the gradient test if and only if the del operator crossed with f is equal to 0. By virtue of this property alone, this particular operator cross product is pretty useful, but it has a number of other physics applications as well. And so this particular expression is sometimes called the curl of f. And so we've just shown that f satisfies the gradient test if and only if its curl is equal to 0. Now, imagine the special case that f is a vector field in the plane. In this case, the third component would be 0. And we could replace f1 and f2 with u and v, respectively. Well, let's follow through what would happen. We'd come up with this. But remember, u and v are functions of x and y, and so the partial derivative of v with respect to z would also be 0, as would be the partial derivative of u with respect to z. And so, in fact, the curl would simplify to the vector del v del x minus del u del y times k. But wait a second, del v del x minus del u del y, that's exactly the expression from Greens theorem. And so we can summarize Greens theorem by saying that the closed line integral of a vector field f dot ds over some contour c is going to be the double integral over the inside of this contour of the curl of f dA, except that the curl is an actual vector, and we only want that component, so we sometimes indicate this by putting a subscript of z here. We just want the z component of this particular curl. And so this is also Greens theorem. Compute the curl of the vector field f equals xzi plus e to the zj plus y times the sine of xzk. So the curl of f, that's just the del operator crossed with the vector field f. So we'll have I, j, k, the del operator, del x, del y, del z, and then the vector field f. The first component is xz, the second component is e to the z, and the third component is y times the sine of xz. And so if we expand along the first column, we'll have I times del y, del z, times e to the z, y times the sine of xz, minus j times del x, del z, times xz, y times the sine of xz, plus k times del x, del y, times xz e to the z. So if we work these things out, we're going to have I multiplying along the diagonals, we're going to have the derivative with respect to y of y sine xz. That will just be sine of xz. Take away the product on the cross diagonal. That's del del z times e to the z, or the derivative of e to the z, which is e to the z. Minus j times, along the cross diagonal, we're going to take the derivative with respect to x of y times the sine of xz. Well, that will be yz times the cosine of xz. Take away the product along the cross diagonal. That would be the derivative with respect to z of xz, which is x. Finally, we're going to have k times the derivative along the main diagonal. The derivative with respect to x of e to the z is 0. Take away the product on the cross diagonal. The derivative with respect to y of xz is also 0. And so this becomes our curl. If we were to clean it up in component form, we're going to have the sine of xz minus e to the z, negative yz cosine of xz plus x, I'm just distributing that minus through, comma, 0. And so here would be our curl. Use the curl to show that the vector field g equals 2xy e to the z plus z, comma, x squared e to the z, comma, x squared y e to the z plus x is conservative. Well, notice first off that the domain of g is going to be all points in R3, because it's built out of polynomials and the exponential function. So this set is simply connected. Hence, to show that the vector field g is conservative, all we need to do is we need to prove that g is equal to the gradient of some potential function. But to show that g is the gradient of some potential function, we could use the gradient test, because we're on a simply connected domain. And the gradient test is the same thing as showing that the curl of g is equal to 0. So let's simply do that. We'll just have to take a curl calculation. So we'll take the nabla operator and we'll cross it with the vector field g. So we'll have I, j, k, del del x, del del y, del del z, and then in the third column, 2xy e to the z plus z, x squared e to the z, and then x squared y e to the z plus x. So we'll have I times del del y, del del z, x squared e to the z, x squared y e to the z plus x, minus j times del del x, del del z, of 2xy e to the z plus z, and x squared y e to the z plus x, plus k times del del x, del del y, 2xy e to the z plus z, and x squared e to the z. And so we just need to work out whether or not this is equal to 0. So our first component will have I times, we'll do the product on the main diagonals, del del y times x squared y e to the z plus x. Well, that just means take the partial derivative. And so we're going to get x squared e to the z plus 0. Take away the product on the counter diagonal, so del del z of x squared e to the z. So that just means take the partial derivative of this with respect to z. X squared comes along for the right of the derivative, e to the z is e to the z. These first two terms cancel, so that's a good sign. Now minus j times the derivative on the main diagonal, del del x times x squared y e to the z plus x. So that just means take the partial derivative with respect to x. That'll get us 2x y e to the z plus 1. We'll subtract that from the product along the counter diagonal. So that's del del z times this expression here. Well, the derivative of this with respect to z, 2xy comes along for the right, derivative e to the z is e to the z, and the derivative of z is 1. And notice that these two expressions completely cancel. Finally, we're going to have k. K times the derivative on the main diagonal. The derivative with respect to x of x squared e to the z is 2x e to the z. Now we'll take away the derivative on the counter diagonal. The derivative with respect to y of this expression. Well, the derivative, the 2x e to the z, will come along for the right. The derivative for y of 1, and the derivative of z is 0. And so that's our second guy. And notice that in this case, we get the vector 0, 0, 0. We get the 0 vector. And so, since the curl is 0, the gradient test is satisfied. Since the gradient test is satisfied on the simply connected domain, we know that this vector is conservative from our equivalent conditions from yesterday. At this point, it might be helpful to summarize some of our basic line integral results. For scalar line integrals, integrals where we have a function of several variables, and we integrate over a curve times ds, we have pretty much one and only one formula for that. The formula that tells us how to compute them as f of c of t times the speed, which is the magnitude of c prime of t dt, evaluated from time equals a to b. That's kind of our one and only formula, but it's worth pointing out that it's independent of the parameterization or the direction of the curve. So for vector line integrals of a vector field dot ds over some curve, we can relate these to scalar line integrals by taking the vector field f and dotting it with the unit tangent vector ds, or using our formula above, this becomes the integral from a to b of f of c of t dotted with the derivative, not the speed, but the actual derivative function, d of t. If the components of f happen to take the form of u and v, then the integral of f dot ds can also be written as the integral over c of u dx plus v dy. If further the vector field happens to be the gradient of some potential function, then the integral of this line integral, according to the vector fundamental theorem of calculus, will simply be the potential function evaluated at the ending point of the line minus the potential function evaluated at the starting point of the line. And we know that f is equal to the gradient of p if and only if f is conservative, if and only if f is path independent, and if and only if the curl of f is 0 on a simply connected domain. Finally, if the curve itself is closed, then the line integral of f dot ds over this closed contour can be expressed by Greens theorem as a double integral of the curl of f's z component dA, where the double integral is taken over the region which is the inside of the curve C. And so this is a summary of our basic line integral results. In fact, this last equation right here, Greens theorem, is worth taking a quick look at, because this last integral is a nice encapsulation of all of the different things we've talked about. Hidden in this description are dot products and cross products of vectors, which are things we talked about at the very beginning of the semester. The actual parameterization of the curve for the left-hand side involves vector-valued functions, whereas the function on the right-hand side represents a function of several variables. Meanwhile, the expression on the left-hand side, which is a vector line integral, can also be expressed as a scalar value line integral, f dot t ds over the same curve, where inside this expression we see one of the components of motion. On the other hand, the expression on the right-hand side involves taking partial derivatives with respect to both of our standard variables. And the only way to attack this is to use an iterated integral, Fubini's theorem. So pretty much every major concept we've talked about this semester has gone into the statement and the execution of Greens theorem. And so this is a pretty fitting place for us to end our Calc 3 discussion. Now let's summarize just some of the fundamental theorems we've found so far. First off, there's the fundamental theorem from Calc 1, which can be expressed as saying that if we were to integrate a derivative over the interval from a to b, that's the same thing as taking f of x and evaluating it that from x equals a to x equals b. We had a gradient version of the same thing. If we take the gradient of f of x dotted with ds, and we did a line integral over some curve, that was the same thing as the function f of x evaluated from the starting point to the stopping point. Now we've got Greens theorem. Greens theorem says that if we have the double integral over some two-dimensional region of the del operator crossed with f, well, at least it's z component, dA, then that would be the same thing as the integral over the outer boundary of f dotted ds. Notice that each one of these things has sort of a common flavor to them. On the left-hand side, you're integrating some kind of derivative of an object. This is the derivative of a function of one variable, the derivative of a function of several variables, the derivative of a vector field. On the left-hand side, you've got the function without the derivative on, and in each case, you are essentially adding up values along the boundary of the shape. If you had the interval AB, then the boundaries would be the points A and B. If you had some curve C, then the boundaries of those points would be the starting point and the stopping point. And if you had, well, a two-dimensional object, then its boundary is precisely this curve right here. So there's sort of a common theme to these things, and this common theme is that if you integrate some kind of a derivative thing over some region, that's equal to some other kind of sum over the function and the boundary of this region. This is sort of a common theme for what are sometimes known as fundamental theorems of calculus. It turns out that there are other fundamental theorems we can do. These other fundamental theorems of calculus form a branch known as vector calculus. And while we're not going to hit them in these series of podcasts, any good Calc 3 book will continue talking about these things. And so I hope you'll take a chance to flip through one of them and learn a few more of these fundamental theorems of calculus. And in the meantime, thanks for listening to these podcasts.